Electrical engineering exam questions. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, linguist, and bilingual teacher of mathematics and physics from Brazil. And in this video, I'd like to invite you to watch the solution of 8 exercises on linear circuits implementing Thevenin's and Norton's theorems. Let's go to the first exercise. Exercise number 1 says, find the Thevenin equivalent circuit for the network of the figure. Also find the voltage and the current at the load. Alright my friends, this is the exercise. Let's go to the solution, and to determine the Thevenin equivalent circuit, we must find the open circuit voltage and the equivalent resistance. Remember that the Thevenin equivalent circuit is this. The open circuit voltage with a resistance. This is the equivalent resistance. Firstly, we're going to calculate the open circuit voltage. How can we calculate the open circuit voltage? We simply open here the circuit at the load. Alright? This is what we're going to do. Let's do it. I'm going to redraw the circuit here. This is the voltage source. This is the 12 kilo ohms resistor. This is 4 kilo ohms. And this is 8 kilo ohms, okay? And to facilitate the resolution of this exercise, we shall use some labels. I'm going to label this current here I1. I'm going to label this current here I2. This current here will be I3. And the voltage at this node, I'm going to call Vx. Okay? And applying nodal analysis, we find that, how do we apply nodal analysis? See that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node, okay? What is the current entering the node? It is I1, and what are the currents leaving the node? I2 and I3, okay? So it is going to be I1 equal to I2 plus I3, alright? How can we write I1 in terms of voltages and resistances? Simply, it's going to be this voltage minus this voltage divided by this resistance, okay? So it is 48 volts minus Vx divided by 12 kilo ohms. And how can we write I2? It is simply the division between the voltage and the resistance. Then it is Vx divided by 4 kilo ohms. And how about I3? I3 is obviously equal to 0 because the circuit is open here. So I3 is 0 amps. Alright my friends. Now it is simple mathematics. I invite you to try to solve it in your house. From this we get that Vx is equal to 12 volts. Okay, this is the first result. And observe that Vx appears here as well. Okay, Vx is equal to the open circuit voltage because as there is no current flowing here, there is no voltage drop on top of this 8 kilo ohms resistor. Then Vx is equal to the open circuit voltage and the value is 12 volts. Alright my friends, Subsequently, we calculate the equivalent resistance. How can we calculate the equivalent resistance? We short circuit the voltage source. Okay, we have to set the forcing terms at rest. And when we set a voltage source at rest, it becomes a short circuit, okay? Then we put a short circuit here. And we write the resistances. Alright, we have to reduce this into a single resistance. Firstly, we're going to combine these two resistances that are connected in parallel. And how can we know that they are connected in parallel? They are connected in parallel because they share two terminals, okay? This is common to this and this is common to this. Can you see? Then equivalent resistance number 1 is going to be 12 kilo ohms in parallel with 4 kilo ohms, and the rule of thumb that we use to calculate the equivalent resistance of a parallel connection is the product over the sum, and this is equal to 3 kilo ohms. And this will be in series with this. When they are in series, we simply add them together. So the total equivalent resistance is 3 plus 8, which is 11. And this is the equivalent resistance, 11 kilo ohms, and this is the open circuit voltage, which is 12 volts. Now we can calculate the voltage and the current at the load because we already have the Thevenin's equivalent circuit. Let's do it. We need to simply use the equivalent circuit. Let's do it. We have here the open circuit voltage, and we found 12 volts. Here we have the equivalent resistance, and we are going to connect here the load, 5 kilo ohms, okay? We are going to call this IL, and this we are going to call VL, alright? To calculate IL, we simply divide. IL is equal to the voltage of the source, 12 volts, divided by the sum of the resistances, which is 16 kilo ohms. And this is equal to 0.75 milliamps. And the value of the voltage at the load is VL is equal to 5 kilo ohms times this current here, 0.75 milliamps, and this is equal to 3.75 volts. And this is the solution of the exercise. The exercise wanted us to find the Thevenin's equivalent circuit and the current and the voltage and the load. Alright, my friends, and this is all for exercise number 1. Let's go to the next. Let's go to exercise number 2. Exercise number 2, find the Thevenin equivalent circuit for the following network. Alright, my friends, this is the exercise. Let's go to the solution, and the exercise wants us to find the Thevenin equivalent circuit for this network. And remember that the Thevenin equivalent circuit is composed of the open circuit voltage and the equivalent resistance. Alright? Therefore, the first step consists of calculating the open circuit voltage between terminals C and D. Okay, my friends? And to facilitate the resolution of the exercise, I'm going to use some labels. I'm going to call this current here I1. This will be I2. This I3. And the voltage at this node, I'm going to call VA. Alright? Remember that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. What is the current entering the node? The current entering the node is I1. And what are the currents leaving the node? They are I2 and I3. Alright. Subsequently, we write the currents in terms of voltage drops and resistances. How can we write I1 in terms of voltages and resistances? I1 is 20 volts minus VA divided by 6 plus 4. Observe that I1 passes here and returns through here. It doesn't pass only through this 6 ohms resistance. It passes here as well. Then it is going to be 20 volts minus VA divided by 10 ohms. Alright? How can we write I2? I2 is VA divided by 10 ohms. And how about I3? I3 passes here, here, and here as well. Alright? 4 plus 6 is 10, plus 10 is 20. VA divided by 20 ohms, okay? And thus, if you calculate, I'm going to invite you to try it in your house, you're going to find that VA is 8 volts, alright? But we aren't looking for VA, we want the open circuit voltage between terminals C and D. And to calculate the open circuit voltage, we can use a voltage divider here. VOC is equal to 10 ohms divided by 4 plus 6 plus 10 times this voltage here, 8 volts, and this is equal to 4 volts. And this is the open circuit voltage. Subsequently, we calculated the equivalent resistance, and to calculate the equivalent resistance, we set the forcing term at rest. Here, the forcing term is a voltage source, and a voltage source at rest is a short circuit. We are going to place a short circuit here to calculate the equivalent resistance. Let me clear the board for this calculation. In the place of the voltage source, the short circuit, here 6, here 4, here 4, here 6, here 10, and here 10, and these are the output terminals. We are going to combine the resistances in series and in parallel. Equivalent resistance number 1 will be the series connection between these two resistances here. 4 plus 6 is 10. And this 10 here will be in parallel with this 10 here. Thus, equivalent resistance number 2 will be 10 ohms in parallel with 10 ohms, and this is equal to 10 times 10 divided by 10 plus 10, the rule of thumb that we use when computing the parallel combination of two resistances is the product over the sum, alright? And this is equal to 5 ohms, okay? And these 5 ohms will be in series with this 4 and this 6 here. And this is equal to 15. Equivalent resistance number 3 is 5 plus 6 plus 4, 15 ohms. And finally, the parallel combination between this 15 and this 10 ohms, the total equivalent resistance is 15 in parallel with 10, and this is equal to 15 times 10 divided by 15 plus 10, and this is equal to 6 ohms, okay? And this is precisely the equivalent resistance. Alright, my friends, and this is the solution of the exercise, the equivalent resistance and the open circuit voltage. Alright, this is all for exercise number 2. Let's go next. Let's go to exercise number 3. Exercise number 3, determine the Thevenin equivalent resistance between terminals A and B. Alright, my friends, this is the exercise. And the exercise wants us to find the equivalent resistance at the terminals A and B. And let's do it. And to solve this problem, we will convert the current source, this current source here, into a voltage source and utilize a test voltage source at the terminals A and B. Firstly, let's convert this current source into a voltage source. And how do we do it? I'm gonna do this in this way. So this is the resistance, and this is the current source, and we are looking for this voltage here, okay? I'm gonna call this voltage Vx. And how can we calculate Vx? Vx is simply the multiplication here. Vx is equal to 200 ohms times 0.1 V1, okay? But observe that Vx here is pointing upwards, but the current flows in this direction here, okay? And it's gonna cause a voltage in this direction. That's why we have to use a negative sign here. Then Vx is equal to negative 20 V1, okay? It is going to make sense for you why I use this negative sign there, alright? I'm going to use this in this circuit. I'm going to remodel the circuit and show to you why I use this negative sign here. Remodeling the circuit and using a test voltage source, we can use a test voltage source here, plus minus V, and here 100 ohms, this will be V1, and here 50 plus 200 is 250 ohms, and here the negative sign means that the polarity is inverse, okay? And here 20 V1. Alright, my friends, using some labels, I'm gonna label this current here I1. This I'm gonna label as I2, and this current here I'm gonna call I3, okay? And remember that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node, alright? So the current entering the node is I1, and the current leaving the node is I2 and I3, okay? I2 plus I3. And we don't know how to write I1, but we know how to write I2 and I3. I2 is equal to this voltage here, V1, okay, V1 appears here, V1 divided by 100 ohms plus V1 plus, observe that they are additive, okay? This voltage here is additive with this voltage. If the polarity was this plus minus here, they would be subtractive, but as the negative sign is here, they are additive, then it is V1 plus 20 V1 divided by 250 ohms, okay? And we have that I1 is equal to this plus this, and we are going to write it in terms of, we are going to write V1 in terms of I1, and we find that calculating, we find that V1 is equal to 10.64 times I1, okay? And this is the value of V1. This is the value of V1, okay? V1 is the voltage here, and we are going to calculate now the equivalent resistance. The equivalent resistance here is different because we are not going to set any of these sources at rest. We can simply calculate, because here we have I1 and V1, and the equivalent resistance is equal to V1 over I1, simply the division of the voltage and the current. And we find here that simply passing here, dividing 10.64 ohms, okay? And the circuit is reduced to, the exercise wants only let me refresh my mind, the equivalent resistance. Then the equivalent resistance is this, and this is the solution of the exercise, my friends. This is all for exercise number 3. Let's go to the next. Let's go to exercise number 4. Exercise number 4. Find the Thevenin equivalent circuit for the network of the figure. Alright, my friends, this is the exercise. Let's go to the solution. As it was said previously, the Thevenin's equivalent circuit will be composed of the open circuit voltage and the equivalent resistance, like this. This is the equivalent resistance, and this is the open circuit voltage, okay? Looking at the circuit, we see that, let's use some labels. I'm gonna label this current here I1, this crossing here I2, and this I3, okay? These are the currents. I1 enters here, I2 goes all the way down here, and I3 all the way down here, okay? And if you remember, the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node, and the current entering the node is I1. And what are the currents leaving the node? I2 and I3, okay? I2 plus I3. Alright, my friends? And I2 is equal to I1 is equal to I2 is the voltage here, okay, on top of the node, which is 200 volts, and divided by the sum of the resistances, 200 volts divided by 100 ohms. This is the value of I2, and the value of I3 will be the same. The voltage on top of these resistances divided by the sum of the resistances. Alright, 200 volts divided by 100 ohms. Alright? And in this way, we find that I2 is equal to I3, and this is equal to 2 amps. Okay, my friends? And I1 is 2 plus 2, which is 4 amps. We've found the values of the current. Now we're going to find the voltages here. This will be Vx, and this will be Vy. Okay? Vx is equal to 20 ohms times 2 amps, and this is equal to 40 volts, and Vy is equal to 80 ohms times 2 amps, and this is equal to 160 volts. Okay, my friends? And Vx minus Vy is equal to 40 volts minus 160 volts, and this is equal to negative 120 volts. Okay, my friends? This is the value of the open circuit voltage. It is equal to negative 120 volts. Okay? If we choose to put X here and Y here. Okay, my friends? If we choose to put Y here and X here, then this would be positive. Subsequently, we find the equivalent resistance by setting the voltage source at rest. Okay? We are going to set the voltage source at rest. And let's do it. Let's set the voltage source at rest to calculate the equivalent resistance. Okay. And here this is 80, this is 20, this is 20, and this is 80, okay? This is X and this is Y. Observe that the short circuit where the voltage source was located is common to all resistances. Observe that this node here is common to all resistances. Alright? Thus, we can redraw the circuit as, I'm gonna put X here, and here will be 80, here will be 20, this will be 20, this will be 80, and this will be Y. The parallel combination is this. The parallel combination between these resistances, the first equivalent resistance will be 80 in parallel with 20, and this is equal to 80 times 20 divided by 80 plus 20, and this is equal to 16. Okay? We have 16 here and 16 here. Sixteen, and ultimately they are in series. If we combine, ultimately we have that it is 32 ohms, okay? Thus, the equivalent resistance is 32 ohms. Alright, my friends, and this is the Thevenin equivalent circuit. A voltage with a resistance, this is the open circuit voltage, and this is the equivalent resistance. Alright, my friends, and this is all for exercise number 4. Let's go to next. Let's go to exercise number 5. Exercise number 5. For the circuit of the figure, find the Thevenin equivalent circuit for terminals A and B. Alright, my friends, this is the exercise. Let's go to the solution. The first step consists of calculating the open circuit voltage. Let's calculate the open circuit voltage, and the open circuit voltage is Vx, okay? And to do this, we are going to use some labels. I'm going to label this current here I1. This I'm going to call I2, and this I'm gonna call I3, okay? Observe that as the output terminals are open, the voltage Vx appears on top of the current source, alright? As there is no voltage drop because I3 is 0, Vx appears here as well, okay, on this node. And if you remember, the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. What are the currents entering the node? I1 and I2. I1 plus I2. And what is the current leaving the node? It is I3, but I3 is 0. Okay. How can we write I1 in terms of voltages and resistances? It is 4 volts minus Vx divided by 2 kilo ohms plus, how can we write I2? I2 we already know, and it is Vx divided by 4,000, and this is equal to 0, okay? And this is simple mathematics. We have everything there, and if we calculate, we're gonna find that it is equal to Vx is equal to 8 volts, okay? To determine the equivalent resistance, we shall make use of the short circuit current, okay? We are going to short circuit the circuit here. We are going to short circuit the circuit here. We are not going to calculate the equivalent resistance directly. We are going to use the short circuit current. Okay, this is a different method. We have here to calculate the equivalent resistance by setting the forcing terms at rest. But now we are going to calculate the equivalent resistance using the short circuit current. Let's do it. Just store here Vx is equal to 8 volts. Okay, I'm gonna have to erase here. And I am going to short circuit it here. I short circuit. And observe that here we had Vx. We had Vx here. And as it is now a short circuit, Vx is equal to 0. Vx was this was the open circuit voltage, okay? This is the open circuit voltage. Open circuit voltage. This was the first value for Vx. But now we have a different situation. Observe that now Vx is equal to 0, okay? It is a different situation, and as Vx is equal to 0, this current here, I2, is equal to 0 because I2 depends on Vx, and as Vx is 0, then this current here is 0 as well. If this current is 0, we know now that I1 is equal to I3, okay? I1 is equal to I3 because the current here, this current source is not contributing with current, then this current here passes there, alright? Alright. Then we have only one current. This current here doesn't exist. This current here doesn't exist. And the currents flowing here will be only one. Okay? This will be only one current flowing from this source to the short circuit. Okay, then the short circuit current, I short circuit, is equal to the voltage of the voltage source divided by 2 plus 3 is 5 kilo ohms, and this is equal to 0.8 milliamps. Okay, my friends, and what is the trick here? What is the catch? Is that the equivalent resistance is equal to the open circuit voltage by the short circuit current, and the open circuit voltage was 8 volts and the short circuit current is 0.8 milliamps, and dividing we find 10 kilo ohms, okay? Consequently, the Thevenin equivalent circuit is 8 volts and 10 kilo ohms. Alright, this is the Thevenin equivalent circuit. Now let's deal with Norton now. Let's go to exercise number 6. Exercise number 6, find the Norton equivalent circuit for the following network. Alright, my friends, this is the question. Let's go to the solution. Remember that the Norton equivalent circuit is composed of a current source in parallel with the equivalent resistance. Norton is different. Norton is composed of a current source with an equivalent resistance in parallel here. This is Norton. Alright? The first step consists of calculating the short circuit current. We are going to short circuit here between terminals A and B, and we are going to calculate the short circuit current here. Alright, my friends, this is how we calculate the short circuit current. I'm going to use some labels here. Again, I'm going to call this I1, this I'm going to call I2, and the current here I'm going to call I3, but observe that I3 goes to the short circuit. I3 doesn't pass through this 10 ohms resistance because it is in parallel with the short circuit. The current is going to avoid this resistance and pass entirely through the short circuit. Alright, my friends? So, again, the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. Okay? I'm going to call this Vx. And the current entering the node is I1. And the currents leaving the node are I2 and I3, okay? How can we write I1? I1 is 30 volts minus Vx divided by 5 ohms. And how can we write I2? I2 we already know, and I2 is 5 amps. And how can we write I3? I3 is simply the division between this voltage and this resistance, Vx divided by 5 ohms. Alright, my friends? Now it is simple mathematics because we have one equation and only one variable, and when we have only one variable in one equation, we can simply calculate, and from this we get that Vx is equal to 2.5 V, alright? And to calculate the value of the current that passes through the short circuit, we divide the voltage by the resistance. Then the current that passes through the short circuit current is Vx divided by 5 ohms. And this is equal to 2.5 volts divided by 5 ohms. And this is equal to 0.5 amps. Okay? Then we already know this. We already know that this current here is 0.5 amps. Okay? I'm going to erase here because now we are going to calculate the equivalent resistance, and the equivalent resistance is calculated in the same way we used to calculate when we were dealing with the Thevenin equivalent circuit. And how do we do this? We simply set this voltage source at rest, okay? then this is going to be like this. I have this resistance, and this resistance here, okay? And here terminals A and B. Okay, this is 10 ohms, this is 5 ohms, this is 5 ohms, and here I had this current source. A voltage source at rest is a short circuit, but I had forgotten, but now I remembered that a current source at rest is not a short circuit as this, okay? When we set a current source at rest, it becomes an open circuit. Alright, my friends, the equivalent resistance number 1 is the series combination between these two, and this is 10 ohms, and the equivalent resistance number 2, the total equivalent resistance, is the parallel combination between these 10 ohms and these 10 ohms, and this is equal to the product of the sum, and this is equal to 5 ohms. Okay, my friends? Consequently, the Norton equivalent circuit is thus, this is equal to 5 ohms. Alright, my friends, and this is all. This is all for exercise number 6. Let's go to the next. Let's go to exercise number 7. Exercise number 7 provided the Norton's equivalent circuit for the following network. Alright, my friends, this is the exercise. Let's go to the solution. But firstly, remember that the Norton equivalent circuit is composed of a current source in parallel with the equivalent resistance. As we did before, we are going to utilize this. There will be a current source here and a resistance, and this is the current of the Norton equivalent circuit, and this is the equivalent resistance. And observe that the Norton current is the short circuit current. Alright? So, we need the short circuit current. The first step consists of finding the short circuit current. For this purpose, we short circuit terminals A and B. We need the short circuit current. And to do this, we are going to short circuit here. And the short circuit current is going to pass here, okay? And I'm going to label this voltage here Vx. And I'm going to call this current here I1. This will be I2 and this will be I3, okay? Alright. And the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. The current entering the node is I1, and the currents leaving the node are I2 and I3, okay? And how can we write I1? I1 is 5 volts minus Vx divided by 5 ohms. I2 is Vx divided by 4 ohms. And I3 is Vx divided by 6 ohms. Okay? This is a simple equation. I am going to invite you to try in your house, and you're gonna find that Vx is equal to 0.513 volts. Okay, and the short circuit current can be found by dividing the voltage by the resistance. Then the short circuit current is equal to Vx divided by 4/6, and this is equal to this voltage divided by this resistance, and this is equal to 0.769 amps. Okay, and this is the short circuit current. We have already found it. Okay, this is 0.769 amps. Okay, 0.769 amps. This is the value of the short circuit current. And now the last step will be to find the equivalent resistance, and the equivalent resistance we already know, and we are going to do the same as we did when we calculated for the Thevenin equivalent circuit. Okay, let me erase it here because I need space. Okay, I am going to set the forcing term at rest. A voltage source at rest is a short circuit. So this is 5, this is 4, and this is 4/6, and these are the terminals A and B, and this is in parallel with this. Equivalent resistance number 1 is 5 times 4 divided by times plus 4, and this is equal to 20/9 ohms, and dot, this will be in series with this, and this is 20/9 plus 4/6, and this is equal to, if we take the lowest common denominator, we find that it is 36. 36 divided by 9 is 4 times 20 is 80, plus 36 divided by 66 times 4 is 24, and this is equal to 2.89 amps. Okay, and this is precisely the equivalent resistance. Okay, this is equal to 2.89 ohms. All right, and this is the Norton equivalent circuit for that network, my friends. And this is all for exercise number 7. Let's go to the last. Let's go to exercise number 8. All right, my friends, let's go to the last exercise. Let's go to exercise number 8. Determine the Thevenin's and Norton's equivalent circuit for the network on the board. Remember that the Thevenin and the Norton are different. The Thevenin is this, and the Norton is this. Okay, all right, they are different. This is the equivalent resistance. Observe that the equivalent resistance is common to both. They are equal, but here is the open circuit voltage, and this is the short circuit current. Firstly, we calculate the open circuit voltage. And how do we calculate the open circuit voltage? We calculate the voltage here between terminals A and B, VAB. And VAB is the open circuit voltage. Alright, my friends? I'm going to use some labels to help us calculate. I'm going to call this voltage here Vx. This current here will be I1. This current here will be I2. And this current here will be I3. Okay? What is the current entering the node? It is I1. Then it's going to be I1 is equal to I2 plus I3. Okay? Observe that as terminals A and B are open, no current flows from the voltage source to terminal A, okay? This is open. This is open. No current will flow there because it is open. Thus, the open circuit voltage will be VOC will be equal to this voltage here, Vx plus that voltage there. They are additive, okay? This negative sign here next to this makes them additive. If the positive sign was here and the negative sign here, they would be subtractive. They are additive plus 100 volts, okay? And how can we calculate Vx? The current of the current source has to flow somewhere, and it is going to flow here. Then we find that as I3 is 0, I1 is equal to I2. The current flows here, then VOC is equal to 20 kilo ohms times 100 milliamps plus 100 volts. Therefore, we conclude that VOC is equal to 300 volts, okay? We already know the open circuit voltage, and it is equal to 300 volts, okay? Subsequently, we calculate the short circuit current by short circuiting terminals A and B, okay? This is the next step. I'm going to erase here for more calculation. And here, there will be a short circuit here, and the short circuit current is going to pass here. All right, my friends? And here, I will call VK just to distinguish VK, because as we changed the circuit, the voltage here changed as well, all right? Remember that I1 is equal to I2 plus I3. Now I1 is not equal to I2, it is different. I1, we know that it is 10 milliamps. How about I2? I2 is equal to VK over 20 kilo ohms, okay? And how about I3? I3 is the very short circuit current that we want to find. But there is a trick here, there is a catch here. It is important to understand this. Observe that this positive terminal here will appear here, okay? And this negative terminal here will appear here. Then Vk is equal to negative 100 volts. Alright? Because Vk is here, and 100 volts is in this direction here, and Vk is the opposite of it. Alright? That's why Vk is negative 100 volts. Then we use it. 10 milliamps is equal to negative 100 volts divided by 20 kilo ohms plus the short circuit current. We can simply divide and pass to the other side, and we find that the short circuit current is equal to 15 milliamps. And we already know this, it is equal to 15 milliamps. Okay, my friends? And to find the equivalent resistance, we simply divide. The equivalent resistance is equal to the open circuit voltage divided by the short circuit current. And if we use the values, 300 volts divided by 15 milliamps, we find that the equivalent resistance is 20 kilo ohms. Alright, my friends, and this is all for exercise number 8, and this is all for this video, my friends. I hope you enjoyed it and learned from it. I'm a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye!